So today we are going to talk about factors affecting enzyme activity. So first one is the enzyme concentration. As we can see in the graph where the x-axis there is enzyme concentration and in the y-axis there is a velocity of reaction. As the enzyme concentration increases, the velocity also increases. That is, they are directly proportional. The rate of reaction or velocity is directly proportional to the enzyme concentration, provided the substrate concentration is unlimited. Next one is a temperature. So here is a graph with temperature in x-axis and reaction velocity in the y-axis. We can see that first there is an upward slope, that is, when we increase the temperature up to a particular temperature, the reaction velocity also increases. What might be the reason? Pause the video and think for a second. Did you get it? That is, it is because when the temperature increases, the kinetic energy of the molecules also increases, which helps them to cross the energy barrier and get converted to product. So up to a particular temperature, the reaction velocity increases. But you can see that after that there's a downward slope. What might be the reason for it? What are enzymes? Enzymes are nothing but proteins. So when we increase the temperature, it leads to the denaturation of these proteins. That is heat inactivation of enzymes. That is why there is a downward slope. So we get a bell-shaped curve. And the optimum temperature is almost always 35 to, or mostly it is 35 to 40 degrees Celsius. So we get a bell-shaped curve. So the reaction velocity increases with temperature until a peak velocity due to increased number of molecules having sufficient energy to pass over the energy barrier. Further, if we increase the temperature, there is a decrease in reaction velocity due to temperature-induced denaturation of enzyme. That is all about the temperature. Next one is something called temperature coefficient. That is, if we increase the temperature by 10 degrees Celsius, by what factor the rate of catalysis increases? Mostly it is 2. That is, the rate of reaction doubles if we increase the temperature by 10 degrees Celsius. It is called the temperature coefficient or Q10. Next one is the effect of pH. If we consider this as an enzyme, this is the active site. Enzymes are nothing but proteins. Proteins are in turn made up of amino acids. Amino acids have H plus ions in them. So these H plus ions present in the active site regulate the binding of the substrate and hence the catalytic activity. Enzymes are proteins and the active site there is H plus, which determines the net charge, which in turn affects the substrate binding and the catalytic activity. pH at which the velocity is maximum is called the optimum pH. It is different for different enzymes. It is mostly 5 to 9, but some exceptions are there like pepsin, which is 1 to 2 is their optimum pH. So this is a graph where reaction velocity is at the y-axis and pH is at the x-axis, and we can see a bell-shaped curve. There is an optimum pH. Increasing or decreasing that pH decreases the activity. Next one is a very important one, that is a substrate concentration. Suppose if we increase the concentration of the substrate, the velocity also increases until a particular point. But after that, we can see that there is no increase in the velocity. What might be the reason? That means only after this point, all the active sites of all the enzymes are occupied with substrate. So further increase in the substrate does not increase the velocity because there is no enzyme to bind with the substrate. So even if we increase the substrate, there is no change in the velocity. So we get a hyperbolic curve. The rate of reaction is equal to the number of substrate molecules converted to product per unit time. If we increase the substrate, the velocity increases until a maximum velocity. Further increase in substrate does not affect the velocity because all of the enzyme active sites of enzyme are occupied. So next is a very important equation, that is a Michaelis Menton equation. According to in the previous slides, previous video we have seen that the Michaelis Menton theory states that when the enzyme combines with the substrate, it initially forms an enzyme substrate complex which splits to form the products and regenerates a free enzyme. This is a Michaelis Menton equation which shows a relationship between the initial velocity and the substrate concentration. In this equation, V0 is the initial velocity, Vmax is the maximum velocity, S is the substrate concentration, Km, that is a Michaelis constant. That is nothing but the ratio of K negative 1 plus K2 divided by K1. So this is a Michaelis Menton theory, that is enzyme plus substrate forming enzyme substrate complex which splits into the enzyme and the product. From this, the Michaelis Menton equation is derived based on following assumptions. The first one is we assume that the reaction is in a steady state, that is the rate of formation of enzyme substrate complex is equal to rate of breakdown of enzyme substrate complex. That is, if we look at this reaction, only one reaction is pointing towards a formation. Both K negative 1 and K2 is pointing towards a breakdown of enzyme substrate complex. That is, if in the steady state K1 into concentration of enzyme into concentration of substrate, that is rate of formation of enzyme substrate complex, is equal to rate of breakdown of enzyme substrate complex. Rate of breakdown means we have to include both reactions, that is K negative 1 into enzyme substrate complex and K2 into enzyme substrate complex. So this is one assumption, and this ratio, that is K negative 1 plus K2 by K1, is a constant called as Michaelis constant, which is called Km. And we assume one more thing, that is V0, that the initial velocity is dependent on this reaction, that is K2 into ES. So these are the assumptions made to derive the Michaelis Menton equation. We are not going to the exact derivation how it is derived. These are the assumptions we make to obtain this equation from this thing. That is a Michaelis Menton equation. Suppose this is a Michaelis Menton equation. Suppose if we are assuming that the initial velocity is the half of Vmax, we substitute that Vmax by 2 in V0 in this equation. The right hand side remains the same. Vmax by 2 is equal to Vmax into substrate by Km plus substrate. We take the 2 here, that is 2 into Vmax into substrate concentration by Km plus substrate concentration. Vmax is common here and here, and we take Km plus S into the left hand side. So Km plus substrate is equal to 2 into substrate concentration. So Km is equal to 2 into substrate concentration minus substrate concentration, that is substrate concentration. This is a very important concept, that is Km is nothing but the substrate concentration when the velocity is half Vmax. Km is what? Michaelis constant. So Michaelis constant is nothing but the substrate concentration when the velocity is half of maximum velocity. So next about the Michaelis constant. That is, it is characteristic of an enzyme and a substrate. Numerically, we have seen that it is the substrate concentration at half Vmax. If the Km is increased, sorry, if the Km is larger, it means low affinity. That means Km is what? Half substrate concentration at half Vmax. So if Km is more means more amount of substrate is need to half saturate the enzyme. That means the affinity is low. Smaller Km means it is high affinity. That is only low concentration of substrate is not needed to half saturate the enzyme. So this is an important concept. That is larger Km means low affinity of enzyme and small Km means high affinity. The next one is a very important one, that is a Lineweaver-BURK plot. When we plot velocity and substrate in x-axis and y-axis, we get earlier we have seen that we get a hyperbola curve. It is very, in this curve we can see that even if we increase the substrate concentration, this velocity does not reach the velocity Vmax, how much ever we increase the substrate concentration. So practically for mathematical purposes, this is a very difficult to calculate from this curve. So what we do instead is that we take the reciprocal of that. This is the equation we have earlier seen, that is a Michaelis Menton equation. V0 is, so we take the reciprocal of it, that is 1 by V0 is equal to Km plus substrate concentration by Vmax into substrate concentration. We split this thing, that is Km by Vmax into substrate plus substrate by Vmax into substrate concentration. When this substrate concentration is common, hence we get 1 by Vmax. If we write 1 by V0 is equal to Km by Vmax, we are just rearranging 1 by substrate concentration plus 1 by Vmax. This is similar to the equation of a straight line, y equal to ax plus b. This is more easier for calculation. Equation of a straight line is more easier to calculate, so we're just rearranging it. We're first taking the reciprocal, then rearranging it. So this is the equation, y equal to ax plus b equal to 1 by V0 is equal to Km by Vmax into 1 by substrate concentration plus 1 by Vmax. So from this equation we have to find x and y. So to find y, we first take x equal to 0. When x is equal to 0, y equal to b. B is nothing but 1 by Vmax. So y equal to 1 by Vmax. Similarly, when y equal to 0, 0 equal to ax plus b, that is minus ax equal to b. X is equal to minus b by a. Minus b by a means minus b is minus 1 by Vmax. A is Km by Vmax. So Vmax is common, so we get x is equal to minus 1 by Km. Slope is a, which is Km by Vmax. So x-intercept is minus 1 by Km, y is equal to 1 by Vmax, slope is equal to Km by Vmax. So this is a graph with 1 by substrate concentration in the x-axis, 1 by V0 in the y-axis, and the x-intercept is 1 by Km, negative 1 by Km, and y-intercept is 1 by Vmax. The slope is Km by Vmax. This is a Lineweaver BURK plot. This is called, so this is a comparison, this is a competitive inhibition graphs. First one is a Michaelis Menton graph. The first one is, in this graph we can see that the Vmax does not change in the presence of the competitive inhibitor, but the Km increases. Km increases. When we come to the Lineweaver BURK plots, since Vmax does not change, minus 1 by Vmax also does not change, but negative 1 by Km, it is more closer towards 0 in case presence of a competitive inhibitor. We have described this in detail in the previous videos. This is non-competitive inhibition. In the Michaelis Menton graph, we can see that the Vmax decreases in presence of a non-competitive inhibitor, but Km remains the same. So negative 1 by Km also remains same, but since Vmax decreases, 1 by Vmax increases. So in summary, in this video, we have seen about the influence of temperature on the enzyme activity, pH on the enzyme activity, substrate concentration. That is what we get hyperbola. We have also talked about Michaelis Menton equation and Lineweaver BURK plot. Thank you.